continuity equation. Now the continuity equation where it is appear in the foundation. Yes.
I'm just wondering, could you upload this to?
No, for this one. And you will notice, well, later on I will show you some example, very quick examples, exactly I extract from the book. And now the, well, I can do a way that still can upload it, but I really am a bit reluctant to, to give you evidence. So sometimes, it's not because of your request. So I promise that I will upload the equation, the useful equations that I showed you last time, that I still will give me some time, then I will upload it. But for this one, okay, I say yes, all right. But I will take away some other stuff that I will show to you here. Okay. But please don't take it, as the the topic or the other things that will directly related to the final exam. I just don't want to have the situation you come to me and then you say that, oh, okay, or your equation that provide to us is actually that's wrong, or maybe I just missed typing a square or something there, and also about this as well. Well, I would say that the study guide would be the whole course. Do you understand what I mean? Is that I just don't want to, well, if you think that that is the, directly related to the final exam, and then you ignore everything outside this, the information that you can hear, then I think it would be a bit risky. But as I said, okay, I will upload this one, okay? But I will just take away some material and I will show you. Because at that point, I just show you. So again, I promise I upload this, okay? But it's not the full version. But now it is your responsibility because when I type something, it's really, I have some kind of mistake. Just make sure that you check and then make sure that if there's some office mistake that I make here, that you just spot it. Well, for intensity, duration, frequency, that information exactly is from the DSD manual. Okay. Well, you don't have to worry. Well, of course, you can write down this kind of equation against. If you don't, then if necessary, just in case that I may also provide in the question. Okay? The question is mainly not to trick you or to check whether you can memorize something or write down something. The double mask analysis, well, we have it in the assignment number 1. Oh yeah, well, one thing I would like to mention is that someone asked me, and actually I may have misunderstood your questions. So to trying to explain this one, and later on I will give you to have a look at the assignment number 1, how we did the calculation. But actually I marked some of the assignment number 1s actually is, well, there shouldn't be any problem so far that I can see. Okay, so I think most of you are okay, but I think maybe some other student may just copy and then they still have no problem. But what I want to say is that we're trying to compare, to check each of the stations with the surrounding, okay, the surrounding station, okay. Now, but the thing is, if there are, for example, 20 stations, well, you don't know whether within that 20 stations, whether there's only one, or there may be 2 or 3 stations will have problem, or even maybe none of the stations have any problem. So what I mean is that when you plot the cumulative curve and you see the slope change, okay? But you can always use all the stations, and then to do one by one, or you pick one, for example, station number 1, and then you use the rest, station 2 to station 20, the other 19, to do the cumulative curve, and then plot one by one. And then the next one you use 2, okay? And then the rest of the lighting to do the cumulative, and then you see the trend. But if you even include all together to plot the cumulative curve in the x-axis, you still find that the difference is not that much. The reason is that if you have more stations, the stations then will have problem even though it's included in it, and then the difference is actually not that much. Now the other thing is you never know. Okay, for example, there are 2 stations have problem. 18 are fine, and you just pick one with problem. Okay, and then you use the rest of the lighting to do the cumulative curve. All right. So you eventually include the other ones with problem as the cumulative. But well, what you can do is that you can plot all the graphs first. It depends on how many stations. Now, just like in our assignments that you got 5, you just do all 5 first, and then identify which one, or maybe 2, okay, have problem. Okay, if you already identified that 2, then you don't use this 2 data for the cumulative stations with data. So then you can isolate the one who may have problem. So again, when I talk about the assignments, then I'll show you again. But remember that you compare with the surrounding station. Now this, well, it's hard to say. Well, anyway, remember how to make use of this free method to find the average rainfall. Okay. So this free, then I cannot rule out. The Darcy laws is very important. Okay. Now this one's already include the continuity equation. V A equal to Q. So without the A here, so that is the energy hat, the energy gradient, and that is the coefficient for hydraulic conductivity. So remember this negative, or sometimes we don't put the negative, then so it depends on this hat, whether it's in the next stage, in the final stage, which is smaller. If it is smaller, then you put the negative sign to compensate the negative sign come out from here. So it's decreasing. So that is the reason why we put the negative sign. So you get to review all this, and remember that we have the different name for the hydraulic conductivity or permeability. So if you just get used to this term, for example, and in the questions that you were given this permeability, then you don't know these two actually means the same things, then you may have problem. Okay, and also the other thing is the unit. Okay, the units of some of the coefficients. So it's better just make it clear. So I don't write it down here. So you need to refer to your notes. That is the reason why I just play safe that everything's in your notes. And more than that, you should do some outside reading. So the these equations, we estimate the drawdown and how it related to the flow rate extract from the well, and also the time. So mostly, we use this to estimate, or maybe how much time is given, and then with this specific flow rate, what would be the drawdown? Okay, it is our concern. Or maybe you just can allow this drawdown, and you want to have this flow rate, and how much time or when this will occur. Okay, so we use this part of the equation. And well hydraulics, mainly the confined and unconfined cases. So you just write down the equation, and remember that from the tutorial. So whether you have 2 observation well or just only 1 well, so at the boundary of the well, so you get 1 boundary condition, and then the other boundary conditions can be go to a certain distance away from the center lines of the well, then the drawdown is almost 0. Okay, but of course when we divide this, we assume that is well, to a very long distance, well, approaching infinity, then the original groundwater surface won't, go down. But well, if for a distance of about 500 meter or 1 kilometer away from the extraction point is already not affected, then you know how to calculate or define the depth of the drawdown or the drawdown or the depth of the groundwater. And the other thing is you need to worry about is the unit. Okay, this too should be the SI unit. Again, as I mentioned, that I won't ask you the English unit question. Okay, so I will, if necessary, I just change, or I will just only ask the question using the SI unit, But again, you need to, know the most fundamentals. Well, there's some simple conversions. So the relationship between cubic meter and liter, right? So milliliter. So I suppose that I don't have to give you this kind of information. So the relationship between kilogram, gram, right, milligram. So I don't have to give you such information, right? So especially one cubic meter is equal to 1,000 liter. So that is the most basic. So I won't give you this in the exam. So now the rational method, that one is actually it's very useful and very simple equations. So as I promised that I will upload this. Okay, so just you don't have to take photos. I will upload this. And again, so if we separate into a number of some catchments, just like the ones that you are doing, then you may do this way. And now these two equations is you can find it in the notes, natural notes, and also can find it in the DSD Stormwater Design Manual. Okay, so just think about how to use it. It's very simple relationship, the name, velocity, and well, if you are given the minimum velocity. For example, again, it's a 0.75 or 0.8 meter per second. Then well, you need to satisfy that. You can maybe, when you do the calculation, you can start with that, okay, as a conditions. Then you change the slope using the Manning equations, and well, you define the Manning end. Well, the Manning end usually is given for different conditions. And the time of concentration. Now remember this one's, well actually, can you remember that I spent a little bit of time to explain this, the rainfall intensity. But that is related to the time of concentrations. Okay, and then quite a number of you came out to ask and clarify the concept. So remember that well, the most remote point, how much time that for the drop of water from the most remote point to come to the exit. Okay, then it takes a certain period of time, right? So it depends on the topographic condition and depends on whether you go into the pipe and then go to the manhole and then another pipe. So how much the flow times it need to take and also the overland flow time altogether. Well, anyway, so you get the time. That time should be the longest. Well, amongst the catchments, or you have a number of smaller catchments. So that time we equate to the time of the durations of the rainfall. The durations of the rainfall. Okay. Now, if you remember that, if you know the duration of the rainfall using the intensity, duration, frequency curve, then you can find the I. Okay. You can find the I. But the main idea is that we equate the time of concentration and durations of the rainfall. It means that over that period of time, we just assume that the same rainfall intensity occur, and there's constant rain, okay, distributing on the whole catchment, okay. So then you get a more conservative result for estimating the flow Q. Okay, think about if it takes 30 minutes from the most remote points to the discharge point. Okay, but the rain just only rain for 15 minutes, just only half. Okay, Then if you use 15 minutes to estimate the I, then it will be different. And the other thing is, if it really, over 30 minutes, even longer than 30 minutes, then the most remote points already contribute to the exit point. So it doesn't really matter if it's continue to rain for 1 hour or 2 hours if everything is the same. Then the same amount of flow will arrive, contribute to the outlet point. That is the main point. That's why we equate, or we need to find the time of concentration first, and then just make it equal to the durations of the rainfall. Then you find the I, okay, the main idea. Well, these equations you can have, you can use for a catchment with the length and then the slope and the catchment area to give a rough estimation of the time of concentration. It means that go to the inlet point. But once you go to the inlet point, so you also say the time of concentration if you have a composite or a different small catchment, and then you use the manual and a number of pipes to connect it together, then you still need to identify the outlet point and what is the total time of concentration. The return period, some simple expressions, and just write down this ones. We mostly will adopt this one to do the calculation. Now, in the case that you get a set of data, or maybe to ask you to calculate the return period or even frequency. Okay, we have a list of the rainfall data. For example, over 50 years, the largest one, second largest, and then the smallest one. Well, if you are asked to do some calculation, maybe the equations will be given to you, but it just depends on how you apply it. Okay. Remember from the notes that we have different expression for this equation. So the probability, and also I think this is the most important one. Now again, so I can make an examples, but I don't think that would be exactly the final exam question. Now, for example, you are asked to do the calculations to estimate the return period. Okay. For a hydraulic structure, we need to construct a hydraulic structures. So with the probability that we can accept is given. So you can do this equation to calculate the return period, right? So can I remember we have the curve, the durations, and also the rainfall intensity, and also there are different lines. Can I remember? Okay. Now, if according to DST manual, so probably you can identify the locations of your design. Then maybe you can select 50-year return period or 25 years return period. Can I remember? Now, maybe you are required to apply this equation to calculate the return period. Okay, and then once you have this return period, then you use that graph, the IDF, then to find the rainfall intensity. So it means that, in other words, you are not given the rainfall intensity. Okay, so just want to show the figures. The rainfall intensity figures. So the time, the durations, and the rainfall intensity. So there are different curves, remember? So for the different return period, T1, T2, T3, right? So what I want to say is that, I just asked you to do the calculation, but the time, the return period is not given. Then you may ask, whether you use this curve, use this one, or use this one, even though you know the duration equal to the time of concentration. So you will ask whether you use this point or use this point. Okay. Then maybe you can use this the given information to calculate the return period. Now, if for the case that we have the 50, 35, or you can have somewhere in between. just like when you use the Moody diagram. So you can approximately find, okay, if it is the one, then you have it here, and then find the rainfall intensity. Then you can carry on to use the rational method. Now the unit hydrograph, okay, I don't include the table here, so just you need to know how to derive the unit hydrograph, and the unit hydrograph is related to the time interval. The time interval. So if you get the flow data, the time interval is 6 hours. Then what you derive for the unit hydrograph is for 6 hour interval. Okay. And if it is 2 hours, then what you derive is 2 hour interval. Okay. Then, when you apply it in the later case, for example, you use the unit hydrograph to derive the direct runoff. Okay. We have the example. Then you need to match with the time interval. Okay. So direct runoff hydrographs. Okay. It's also required that you need to review it. So as I mentioned, the river routing. So remember all this equation, okay? So you just check. Make sure that you write correctly the equations. Don't miss out anything. How to find K and delta T. So in your assignments, again, most of you actually did quite well. So there shouldn't be any problem. I will go through about that. And the reservoir routing, remember all those equations, and mostly you need to use the table, okay, to work out the result. The discharge, I also include one equation here. So it doesn't mean that the other equation is not important, because this one shows you the stage. The flow rate and the depth, right? Okay. So maybe you are required to use this information to link with the reservoir routing. Okay. So remember that we have the storage and how it related to the water depth, and then how it related to the outflow. Okay. So you may also require this information as well. Okay. Then for the hydraulics, I will ask the question that is more practical rather than too theoretically. Okay, so even though you see the examples included in this chapter, the fundamentals of hydraulics, is actually look a bit complicated. The reason for that is simply because the unsteady term. Now, but when we do the real application, the pipe flow, except the transient flow, okay? But for the transient flow, we can, also to a certain extent that we can consider that is steady. Well, can you remember that once we design the control volume, which move the same speed as the weight or the pull, then we change it to a steady case. So mostly you deal with the steady flow situation, pipe flow or the open channel flow. Okay, but still, I think you better also review this chapter. So to write down all this equation as well, okay, the continuity equation, then eventually, it reduces to that very simple form. The momentum equation as well, okay. And I mentioned to you that, now just by this example, I'm not going to include in the version that I upload to the campus. This one's actually I already explained to the class. Just to remind you, I'm not going through in details. The two we here, right? One is related to the total mass flux, and then the other one is related to the directions of the force. Okay, so then this example just trying to demonstrate to you, okay, for some extent that if you consider the x component, so there's a velocity v component, okay, in this direction. But the velocity to calculate the total mass flux or total flow rate, then you don't need to use this component. Remember, right? So that is to remind you the momentum equation. The energy equation is well, it's very useful. Then remember the pumps, whether we have turbine, okay? So you know all this, and the correction factor. But I won't ask you for the case that you need to use difference correction factor. So you just assume that okay is equal to 1. Okay, but for real application, remember. So this is not the only equation that you universally apply. So you gotta be careful. Okay, if it is not turbulent flow, it's laminar flows. Okay. Now another example is that well, for example, you may deal with the pipe flows, the valve. So major laws, minor laws, also things, okay? And how you apply these equations, okay? And remember, I emphasize, okay, about here and the outside here, the atmospheric pressure. So when we deal with the energy equation, the pressure term, what kind of pressure that we define or we use? We use gate pressure. So the gate pressure, again, about the atmospheric pressures, okay? Now, and also for this case, can you draw the hydraulic gray line, energy gray line? So can you also analyze the pressure inside, which is the lowest pressure point in this case? So then the minor laws, major laws also thing. Now, just like this, well, because I copy this from the book. So it's cannot distribute to you. That is the reason why I will take this away. Now you see this example that draw the energy gray line and hydraulic gray line. So if you remember that, okay, now these two, well, they have the same distance separate apart, and these two also, but there's a point B here. So what happened to point B? And why the difference between the energy gray line and the hydraulic gray lines reduced? Okay, and why this hydraulic line come to connect to the exit here, and why there's a drop here? So there something here. Well, the solid line represent the energy gray line, hydraulic gray line is the dotted line. Now, so at point B, there's an expansion joint here. So what was the meaning of expansion joint? It means that the pipe in AB is smaller than pi in BC. So the pi diameter enlarged. And you have the steady flow rate Q, and the velocity V reduced. So the velocity had reduced. That is the reason why you see these two lines, the difference is not as much as these two. So you may not be asked, in some questions that to do the calculations of the energy gray line and hydraulic gray line. But you may ask to explain why the line would be like this. What possible cause to make this to happen? Okay. Now the other point is, well, the where is the maximum pressure? Where is the minimum pressure? Okay. Now for this one, the minimum pressure is SC, and why it is SC? Now without seeing this, well, the answer, can you identify the highest pressure point and the lowest pressure point? If we change this sketch, but provide to you the hydraulic gray line and energy gray line. Okay? So then, well, just remind you, through pipelines, major laws, minor laws, then well, there are two equations to estimate the major laws. Okay? And remember, the friction factor is always functions of the Reynolds number, the relative roughness, so the iterations. The Hazen-Williams equations also that you can use, but remember that this power 1.852, and if you use this one, you can change to the flow rate Q, and the power is equal to 2, right? So the Moody diagram, then well, you kind of knows how to use it. The branch price systems, okay, well, it's very good. I think it's very easy, to make up some difference pilot works using different numbers of the reservoir or the tank, and then to prepare the question like this. So what the junction point, what is the elevation, and also what's the flow rate, okay? Now the other thing is when we have pi in series, so the flow rate need to be the same, okay? But the head losses are accumulated, so because different name, so you probably know it. And but when we have pi in parallel, so the flow Q1, Q2, Q3, they are accumulated, so add up together, become a total. But the point here and here, the head loss will be the same, right? So, well, then we apply this concept in the pi network, and I think you did it in the assignments. So this equation that you need to write down. Also, although I do not guarantee that whether there will be questions to calculate the pi network in the exam, but just write it down. Just write it down, the equation. So the pump, okay. Now this is important. Okay, how to find the operating point. Okay, so you can use graph. Okay, the efficiency. So pump in parallel, in series. So you can also write down this curve, this graph, if you want. Okay. And to write down the point that what is additive, what is the same in parallel, okay? So this graph. Calculations, well, I think it's not that important in this case, but you can again write down all this equation, but you just need to understand under what situation the calculations may occur, okay? Now the water hammers also, you better write down all these equations. So again, I will upload it. And now remember these four figures. Okay. Now again, so I can the same as the natural notes. You see this curve up and down. Okay. Now this one is actually asked about the pressure at this point at the gate wall. So if just change the pressures, so giving you the flow velocity, or you can calculate the flow velocity, and then okay. What is the pressure change over a certain period of time at the midpoint, or 1/3 of the distance from the exit? So you will finally get a similar drawing like this, but actually it will, the whole thing will shift. Now, of course, if you are given the numbers, then you can, draw it on scale. Okay. So remember that it's not necessarily exactly the same. This just only applies to the case that when you ask you about the pressure at this gate, and then you just prepare maybe some question to ask you at different location. And this one will not be included. So the open channel flow, also things, and the many equations, just the equation you need to write down. Okay, you need to know how to apply. You need to know how to sketch the energy gray line, hydraulic gray line for the open channel flow case. For the open channel flow case, you may need to do the calculation first, and then there may be fine mark to require you to sketch this hydraulic gray line and energy gray line. Okay. Now the best hydraulic section, remember. So you know for the rectangular channel. But I don't know whether you try or you go to the internet to find the case for the trapezoidal channel. So that is related to the size law. Okay? So you can always find, or you can derive it by yourself. Okay? The best hydraulic section. So the other thing is the non-uniform flow. Remember this very important, specific energy. Specific energy. How to calculate the flow number, and also things like now the profile. Okay, M1, M2, M3. You can find it in the notes. S1, S2, S3. Now this one's again you can find from the library, the book. So if you are given The line here, okay, this line, the dotted line here, so the normal depth, critical depth. So you are asked to identify the flow, the profile. So the mild slope, steep slope, change to mild slope, there's the four here. So then you need to identify, okay, that is a change from mild slope to steep slope. So we have the M2 connect to S2, remember? And well, when there's a case here, we have the Sudas case, which is lower than the critical depth. So you have the S1 here, and then the hydraulic jump. And the other case, hydraulic jump, M3, M2. Okay. Now the other thing, can you remember is that I told you already, the flow rate is steady. It doesn't change. So for different slope, you will have different critical, different normal depth. But the critical depth is always a constant. Always a constant. So the distance from here is always constant. Because you just check the equations, the critical depth, it just only functions of the flow rate. So unless you change the flow rate to the other case, then the YC won't change. Okay? So remember this. Then that one is the direct step method. So the direct step method. So to calculate the distance, you can I guess write down this one. The hydraulic jump, that is the hydraulic jump, but that is the theory and the equations that we eventually come up with these two equations, okay, and also the energy loss, this sort of things. Now the assignment number one is actually there's no I don't see any problem with many of the submissions from you, but against that for 5 stations, well, it depends. You may not be necessarily the same as me, and I also find the calculations from some of the students actually the final result. So most of you did the calculation of, well, many of you actually used the summations of the 5 stations. So well, that's fine. As I explained that you can identify which one first. So in this case, it's mainly the station number 1 has problem. But in the case that maybe station 3 also had problem. Then when you work on station 1, then you still consider the station 3 in the summation as well. Then, as I said, that you may do the screening first. Whatever you use, 5 stations or you just only use the rest of the station. Do a screening first, and then you identify maybe there are 2 or 3 stations amongst the whole group of the stations have problem. Isolate them, and then don't use them as the cumulative result. So anyway, well, you plot it, and you find mainly the station ones, some deviations, and then the rest actually still more or less a straight line when you calculate the cumulative and annual rainfall and all the stations. That is the remaining station, and then the ones we plot. So someone identifies 1977, someone 1979, someone identified 1978, still fine, okay? So because there's, I know sometimes it's a bit difficult to tell, but and the other thing is when you calculate the slope, I also see the difference. So not very big, but eventually when you come up with the ratio and then adjust the result, then the result will be a little bit different. Okay, someone calculated 34 or 30 something, I cannot remember. But still, okay, that is not the point that I deduct marks. Okay, so you just calculate the average. For question number 2, actually, most of you have no problem. Well, just quickly go to the points x equal to 0.1 and then you calculate the k, right? The k's are almost equal to 3 days. Right? For question number 3, well, actually, I think most of you are correct. But I just find the case that maybe the careless mistake of someone's write the result equal to 0.071, so 1 0 is missing, and maybe some careless mistake or. But for the B and 3, so the X and the hydrogen gradient, so there shouldn't be any problem. And now for this ones, well, you do a very simple way, but still the answer is correct, and you use the geometry to do the calculation. There's nothing wrong with it. But if you see my answer, then for this one, now because this one is like a triangle, so we have two triangles combined together, so you can use the geometry. But if it is not a triangle, so I give you a certain profile, so it's a curve here, then you may not be able to use a simple geometry to calculate, okay, this area, okay, to estimate the mass flux. So in that case, you should do like this. So the small change, and then you can go from the center to the point that is R, and that is dr, and all together with 2 pi r, you calculate the area. So you should use the integration to do it. Okay. But anyways, well, you did it correctly. That's no problem. But I just remind you for some other cases that if the geometry is not as nice as this, then you need to use the integration. So eventually, everybody get 1.19. Okay. Well, for the question number 2. So it depends on the iterations that you use, and you all submit it, right? Well, then, well, show it to you later. Well, the result may not be exactly the same as mine, but there may be some a little bit difference. It depends on how many iterations that you do. Okay, and well, the directions, it depends on how you define it. So, but anyway, when you finish the calculation, you should be able to check whether it can satisfy the continuity equation or not, and satisfy the energy equation. If you can satisfy it, it means that your result is correct. You don't have to, check with my answer. And for question number 2, well, it's pretty much straightforward for part 1. And now the thing is, well, we changed from a rectangular channel to a trapezoidal channel. Okay, the point, well, anyways, well, use the critical flow conditions because when it come to here, the critical flow conditions occur. So remember that, be careful when you calculate the critical flow depth, okay? Well, you can calculate the normal flow depth and then find the difference. For part B, you just, well, you don't know how high you rise. So the data is set here. And then just add up the water depth. So it will fix or confined by 5 meters. Then you just plug into the specific energy equation. Then you can calculate this. Okay, about 1.34.